Now we are going to see some problems based on IR spectroscopy. To solve the problem, let's revise about the Hooke's law. We have studied this Hooke's law where the frequency is directly proportional to 1 upon 2 pi c in square root of f upon mu, where f is nothing but a force constant and mu is the reduced mass. Okay, so here the frequency is directly proportional to force constant and it is inversely proportional to the reduced mass of the atoms. Now this force constant is directly proportional to bond strength, which is inversely proportional to bond length. Means bond length is shorter, more is the bond strength, more is the force constant, means more is the absorption frequency. If bond length is more, bond strength decreases, force constant decreases, absorption frequency decreases. We have to remember this relationship while solving the problems. Okay, now another thing is how to calculate the sites of unsaturation while solving the problem. So for that, the rule is that if molecular formula contains the oxygen or sulfur atom, each oxygen and sulfur atom is neglected, each nitrogen atom is replaced by CH, each chlorine, bromine, iodine atom replaced by the hydrogen atom while solving the problems. Okay, now here is the first problem. Molecular formula of the compound is C3H6O. It shows the band at 1720 centimeter inverse and 2720 centimeter inverse in its IR spectra. Find out the structural formula of the compound. So first we want to find out the site of unsaturation. So here in this molecular formula C3H6O, we have to neglect the oxygen atom and the molecular formula becomes C3H6. Okay, now in this C3H6, it contains the 2 hydrogen atom less than saturated hydrocarbons. Saturated hydrocarbons have the molecular formula CnH2n plus 2, where n is equal to number of carbon atom. Here number of carbon atom is 3, so replace it by 3. So 2 into 3 plus 2, which is equal to C3H8. Okay, so the saturated hydrocarbon will have the molecular formula for the 3 carbon is C3H8. Now here in this C3H6O, it contains the 2 hydrogen atom less than this molecular formula for the saturated hydrocarbons. So 2 hydrogen atoms less means there is a one site of unsaturation. Okay, so first always you have to first find out the site of unsaturation while solving the problem. Now the second important point is the IR bands are given. So this IR band at 1720 centimeter inverse indicates the presence of carbonyl functional group. It may be aldehyde, it may be ketone. Okay, but here another band is also given which is at 2720 centimeter inverse. This indicates that this is due to the aldehydic CH stretching. We know the molecular formula for the aldehyde, that is C double bond OH is there in general formula. So this aldehydic CH stretching, it generally appears at 2800 centimeter inverse. So here the frequency is 2720 centimeter inverse. So it is confirmed that there is aldehydic functional group is present, and as aldehydic functional group is present at the one end, so as it contains the 3 carbons, so first write down the 3 carbons. Let's say, see here like this, 1, 2 and 3. Out of these 3, one is aldehydic functional group. Now replace another one or fulfill the valencies of the carbon. So here 2 hydrogens are required and here 3 hydrogens are required. So this is the structure of the molecule, and this appears at 1720 centimeter inverse while this appears at 2720 centimeter inverse. So in this way the structure of molecule is nothing but a propanaldehyde or propanol. So in this way we are going to solve the next problems. Okay, so always remember we have to first find out the site of unsaturation. Okay, and if some reasons are asked, for example here in case of cyclic ketones, okay, as the ring size decreases, here cyclohexanone, cyclopentanone, cyclobutanone and cyclopropanone, as the ring size decreases, angle strain increases. Here ring size decreases, angle strain increases. As angle strain increases, carbonyl stretching frequency increases. So if we want to see the values for it, then here for cyclohexanone the carbonyl stretching frequency is 1710 centimeter inverse. For cyclopentanone it is higher, it is 1740 centimeter inverse. For cyclobutanone it is 1775 centimeter inverse, 1775 centimeter inverse, and for cyclopropanone it is 1818 centimeter inverse. So what is our observation? As ring size decreases, angle strain increases, and as angle strain increases, carbonyl stretching frequency increases. Another important point is about the hydrogen bonding. We have seen in applications of IR we can detect the hydrogen bonding. If hydrogen bonding is intermolecular, then this OH stretching frequency it decreases. Okay, the normal value for OH is 3200, it is about 3600 centimeter inverse, and when it is hydrogen bonded it comes near about the 3200 centimeter inverse. But if there is a such type of intermolecular hydrogen bonding is there, then on dilution these molecules goes away from each other and stretching frequency increases from 3200 to 360 centimeter inverse. And if the hydrogen bonding is intramolecular, for example here in case of salicylic acid, so it contains the intramolecular hydrogen bonding. In that case on dilution there is no change in the OH stretching frequency, it appears at 3200 centimeter inverse, and on dilution also there is no change in absorption frequency, it occurs at 3200 centimeter inverse only and not at 3600 centimeter inverse. So we can detect whether the hydrogen bonding is intermolecular or intramolecular. Intermolecular hydrogen bonding increases on dilution, while in case of intramolecular hydrogen bonding there is no change in absorption frequency on dilution. Okay, so these are the some points you have to remember. Now the next problem based on the IR spectroscopy is again the molecular formula is same, only IR bands are changed. It is C3H6O, IR band given are at one is 3300 centimeter inverse, then another band is 1620 centimeter inverse, 990 and 910 centimeter inverse. Now we have to find out the structure of the molecules. So first is site of unsaturation. Always remember you have to find out the site of unsaturation, and for this molecular formula we have already find out the site of unsaturation. It contains 2 hydrogen atom less, so there is a 1 site of unsaturation. Now the second point, the IR absorption band at 3300 centimeter inverse. Now it may be due to OH, it may be due to NH, or it may be due to carbon-carbon triple bond CH. Okay, this stretching. So here in this molecular formula, as there is no nitrogen atom is there, the presence of NH is ruled out. Okay, as there is only 1 site of unsaturation, so presence of carbon-carbon triple bond, this CH stretching, it also ruled out. So what is remaining? Only the OH. It may be a alcohol. Okay, now the IR band at 1620 centimeter inverse indicates the presence of carbon-carbon double bond in the molecule. Okay, and the IR band at 990 and 910 centimeter inverse is due to the mono substituted ethylene group, that is CH2 double bond CHR. Okay, and according to these our findings, we can conclude about the structures of the molecule. So there are 2 structures can be suggested. So as carbon-carbon double bond is present and OH is present, so this may be the possibility. And another one is that CH2 double bond COH CH3. Okay, but this can be tautomerized like this. So after tautomerism it forms nothing but a acetone, and if this is the possibility, then it must show the carbonyl stretching frequency at 1720 centimeter inverse. But as there is no carbonyl stretching frequency, the possibility of these structures to is ruled out. So what is the possibility of the structure? So structure 1 is the correct. So it contains an unsaturated alcohol. Okay. Now the next problem, the molecular formula is C4H6. C4H6. Now it shows again the band at 3300 centimeter inverse, and the next band is at 2100 centimeter inverse. Okay. Now for this, the site of unsaturated for saturated hydrocarbon, the molecular formula becomes for the 4 carbon, replace N by 4. So C2 into 4 plus 2, which is equal to C4H10. So this is the formula for saturated hydrocarbon. So it contains 4 hydrogen atom less than this. So it indicates the 2 sides of unsaturation. Okay. Now again, the next probability of these 3300 is there must be OH, there must be NH, or this terminal alkyne CH stretching. Okay. As there is no oxygen, possibility of OH is ruled out. As there is no nitrogen, possibility of NH is also ruled out. So what is remaining? There must be presence of carbon-carbon triple bond. Okay. So the IR band at 3300, it is due to this carbon triple bond CH stretching, and it also shows band at 2100, which is due to C triple bond C stretching. Therefore the possible structure of the molecule is 4 carbons, 1, 2, 3 and 4. So one is triple bond, it contains the terminal alkynes and fulfill the valencies by the hydrogen atom. So molecular CH3, CH2, C triple bond CH, 4 carbons, 3 plus 2, 5 plus 1, 6 hydrogen atom. Molecular formula satisfies the structure. This appears at 2100 centimeter inverse, while this band is appears at 3300 centimeter inverse, which is for the terminal alkyne. So this is the structure. Okay. Now the another type of problems where we are going to distinguish some molecules by using the IR spectroscopy. For example, phenyl acetic acid and methyl benzoate. First you have to draw the structures. Okay. So the structure of phenyl acetic acid, this is phenyl acetic acid. CH3COOH is acetic acid. One of the hydrogen atom is replaced by the phenyl group, and the another structure is methyl benzoate. So this is the structure which is a ester. Okay. Now we can distinguish it by the IR. First is both showing the carbonyl stretching frequency, but this carbonyl of carboxylic acid, it appears at 1700 to 1725 centimeter inverse, while this carbonyl for esters appears at somewhat at higher frequency, which is 1735 to 1750 centimeter inverse. And the second band, first is distinguishing point of carbonyl, and the second point, it is this shows the OH band, which is present only in carboxylic acid near about 2500 to 3600 centimeter inverse, and it shows the COC stretching, which appears at 1180 to 1300 centimeter inverse. So in this way we can distinguish between these two molecules. Similarly, another pair is given, for example benzyl alcohol. So here it shows the band for OH at 3200 to 360 centimeter inverse, while the another compound is benzaldehyde, and in this benzaldehyde it shows the band for the carbonyl stretching frequency near about 17 centimeter inverse, and CH band is near about 27 to 2900 centimeter inverse. So in this way we can distinguish between the two compounds by using IR spectroscopy. So we have finished with this IR spectroscopy. In the next lecture we are going to start with the new chapter, that is NMR spectroscopy.